So hi once again, and welcome to today's webinar about additive manufacturing for plastic injection molding tools. So to start off with, I would just like to show you how the program works and how the webinar works. So you might have noticed that all of you are muted, so I'm the only one who can talk. But on the right, you have a dashboard with a small arrow. So if you click the arrow, then you can write questions to me. And the questions are anonymous, and I will answer them all at the end of the webinar. So if you have any questions, please type them to me anytime, and then I will answer them at the end. Okay, so the agenda for today, I will start with an introduction where I will introduce how we work as a company. And then I will go over to material, what material we prefer for additive manufacturing for plastic injection molding tools, and show a customer case here. And then I will proceed to talk about CAD and CAM and how to start the process of additive manufacturing, and then also show a customer case, how we work here, and then move forward to design and simulation, show a customer case, some post-processing, and then continue with various customer cases. So to start off with, I would just like to show the process chain of how we work. So we would like to participate in the entire chain. So at the beginning, we like to discuss which material to choose. And here we produce the powder in Sweden, in Hagfors. So at the mill in Hagfors, we produce the powder that we use for additive manufacturing, just as we produce conventional grades. So we produce the powder, and then we like to talk about which material to select for different applications. And this is how we work conventionally, and this is also how we work with additive manufacturing. The next step for additive manufacturing would be to discuss the actual 3D model. So often when you talk about additive manufacturing, you say that you can print everything. And that is somewhat true. You can print a lot, but some parts are better to print and some parts are not so good to print. And often you can just do small design changes and then they will be more suitable to the process. So we like to join you for visits or phone calls in an early stage just to discuss how the 3D model looks like, or even check if this is the right area to print. And today we will of course talk about additive manufacturing for plastic injection molding tools. And this is often a great area. Not always, but often it works out really, really good. So the next step in the consulting would be design and simulation. We do not design or produce entire tools, but we do help with redesign for the additive manufacturing process, as I talked about earlier. But we also do redesign of cooling channels, so something that we call conformal cooling. And why do we do this? Well, often when you turn to additive manufacturing for plastic injection molding, it's because you want to maybe decrease the cycle time or improve the quality of the produced plastic part. And you do that by improving the cooling channels. So you want to have a uniform cooling, even cooling in the tool. And that's where we can support you guys with different simulations or redesign just the cooling channels so you get the right uniform cooling that you need for your tool. And then we move on to the AM process. So in the beginning, our aim was just to produce powder and be a supplier of material as we are today. But the problem is that there aren't too many printing companies out there. So we have also invested in multiple machines. So today we have 7 different machine centers around the globe where we can help you to print inserts or dies directly to you guys. So in the AM process, we can also help you with printing parts, but also develop parameters for different machines. Hybrid manufacturing is something that I will discuss more later on. And the last step is, of course, post-processing. So we do some machining. Otherwise, we have other customers that we can recommend to machine the part for you. So this is something that we can help with. But we do have in-house heat treatment facilities, and we also work a lot with coating and quality assurance within our group. So with that said, I would just like to show where we have our additive manufacturing centers. And for the north, I would say that we mainly print everything in Düsseldorf. So here we have a center where we print parts directly to our customers. And in Hagfors, Sweden, we produce the powder. In Hagfors, we also have a printer, but that's mainly for R&D. So this printer is not used for customers directly, but more to develop new grades and develop the grades that we already have. And then you can see that we also have centers all around the globe. And of course, we can use these as well, but we mainly use Düsseldorf, to be honest. We are focusing on 2 different methods, so both laser beam melting and direct energy deposition, which is also called laser cladding. Today, we will mainly talk about laser beam melting because this is the process that is mostly used to produce tools with conformal cooling. So all tools and inserts for injection molding are mainly produced in this method. You can also see that we have various machines and also different brands. We have also had other brands before, Trumpf, SLM machines. So we are not bound to one brand. We like to try them all and see which machine that works best with different grades. So one thing that is always good to discuss is the size of the machine. Because this could be a limitation, because you see even one of the biggest machines that is 400 times 400 times 400 millimeters is quite small if you talk about the tool. But remember, we often print inserts because it's inserts in plastic injection molding where you often have problems with heat affected zones. So I would say that the printing size is actually not a limitation when it comes to plastic injection molding tools or inserts, because it's not that often that the inserts are bigger than this. So then let's move on to material. And I would like to introduce Udholm AM Corax. I suppose that some of you have already tried it or at least heard of it before. But when it comes to additive manufacturing, it's really suitable due to that it's easy to weld. So that's a general term. If you can weld it, you can print it. That's very general. But for Udholm AM Corax, it works great to print. And if you then go to plastic injection molding, then Corax is really good due to its corrosion resistance. So if you have any corrosive plastics or additives, then Udholm AM Corax is really suitable. Or if you use bioplastics, which is a starting trend right now, there we have seen that a lot of the bioplastics on the market today are quite corrosive. So then Corax could also be a solution. Transparent plastics where you need high polishability, then Corax is absolutely a good choice. But I would say the main reason to go for Corax is for the cooling channels. So if you go for additive manufacturing, then once again, you probably have quite complicated cooling channels. And here you don't want to have corrosion because they're quite hard to clean. So in order to avoid corrosion in the cooling channels, then you can just choose Corax and that won't be a problem. And last but not least, it's also a NormPack certificate. So you can use it in direct contact with food. It's even certified for one step further. So for medical applications, you can actually use it in direct contact with the human body. So you could use it as a transplant in a human body. But I won't talk about that too much today. And after printing it, it has a hardness of 34 Rockwell, and you can age it to a hardness of 50 Rockwell. You can actually deep cool it to maximize the material as 52 Rockwell, but 5th is usually what we aim for. So we also have Corax as a conventional forged material, and here you can see the mechanical properties of the forged material, and here we have compared it with the 3D printed material. So just to show you that the 3D printed material has very equal properties with the conventionally produced material. So produced vertically or produced horizontally, that's just if we are doing the tests with or towards the layers in the print, just to show that there are equal properties in both directions. So I mentioned before that Corax also has a really good polishability, and here we are comparing it with the material that is called 1.2709. And the reason why we are comparing it with this material is because 1.2709 is a really common material to print. So the pictures that you see here are polishing samples where all the black dots are defects on the surfaces. So you do not want to have any black dots. So to start off with, we can look on these two pictures. Here we have the material 1.2709, and the samples are printed in a machine from EOS, the M290 machine. And you can see you have some black dots. It's still a quite good sample. But then if you compare these two pictures with these two pictures, then you can see it's the same material. It's the same supplier of material, but we have changed the machine. So here you can see directly that different grades goes along better with different machines. So if we once again look at the EOS M290, but we change to Corax instead of 1.2709, so same machine, different material, then you can see directly that the polishability of Uddeholm AM Corax is quite high. It's so high that you can even compare the printed material with the conventional material, and there's not a big difference. So the main difference is that in the conventional grade, you have some more black dots, but they are smaller in size. And in the printed part, the defects are not as many, but if you get the defect, then the chances that the defect is somewhat bigger in size. But still a really, really good polishability of the material. So before going into NormPack, I would just like to say that I see that we have some more attendees right now, and I would just like to say that everyone is muted. So if you have any questions, then you can write them to me. You have a dashboard on the right side where you can click an arrow, and there you can ask anonymous questions, which I will answer at the end of the webinar. So if you have any questions, just write them there and I will answer them later on. So what I said earlier, NormPack is certified for food. So if you've ever seen this logo before, it means that the product is certified. So you can use the product in direct contact with food. And here you can also see that Corax is actually certified to be used directly with food. So this is not always important for plastic injection molding because the steel is only in contact with the plastic, and then it's actually the plastic that is in contact with the food. But some companies also want to have a NormPack certified material for creating plastic parts as well. So to show you a customer case when we have compared two different materials in the same application, this is a quite small insert where the original insert was created in 1.2709 and a hardness of 48 to 50 Rockwell, and it cracked after 400,000 shots. And the reason is because the 2709 is not corrosion resistant. So you can see here that there are severe corrosion in the cooling channels, which led to small cracks between the cooling channel and the surface of the tool. So if you look on the tool on the outside, it looks perfect. There's no corrosion on the outside because there were no corrosive plastic or additives. but the corrosion on the inside in the cooling channels resulted in small cracks that was cracking the tool. So we changed to Corax instead, same hardness, but we haven't seen any cracks so far, and the tool have run for over 740,000 shots. But it's still in production, so we don't really know the lifetime of the tool, to be honest. And the next step is 3D modeling. So this is where we check the feasibility of the part, or we use just knowledge that we have before and see if this is a good part to produce for additive manufacturing or not. So here we would like you to reach out to us as soon as possible in a new project or a ongoing project. So before you design too much or you put in too much effort into the part, please discuss it with us, and we can see if we have printed any parts similar to this before, or if we know that this is an area that won't work, or if we know that it's an area that is perfect for additive manufacturing. And then we can go through some more rules for additive manufacturing that you should think about, so that we can print it in the best quality possible. If you already have a part, then of course we are also happy to receive the CAD file, and then we can go through the CAD file step by step together with you and discuss some pros and cons with the design. Hopefully only pros, and just talk with you about how to design the support structure, and of course we will do that, and also how we would orient the part for the optimal quality. So the second thing we would do is also to discuss the opportunity to maybe build a hybrid tool. So a hybrid tool is when you first produce a bottom part of the tool in a conventional manufacturing way, so maybe by a CNC machine, then you produce this part, and then you can send it directly to us, and we put this lower part into the machine, into the AM printer, and then we only print the top part. So here we can both save time and we can save money. So we're using the right manufacturing technique for the right process. So CNC this part, put it into the additive manufacturing printer, and then we print the top, the complex geometry, so to say. And then we go on to talk about support structure, because it's really common that you have to use support structure. And for you who don't know what support structure is, then I'll just go through it quite briefly. And it's all surfaces that don't have any steel underneath, they cannot be created. So for this surface, for example, there's nothing underneath here. So imagine that the part is built by layer, so from the bottom up. And when you come to this layer, nothing underneath will support this part. So here the printer would need to add something that we call support material, or we don't call it support material, it's actually the general term. But support material is the same steel grade that we're using to produce this part, but it's printed in another way, you could say. So we have some other parameters to print this material. But still, all surfaces that don't have any support underneath need to have support material. And this also goes for very tilted areas, like this one. Here the machine would also add support material, but also in the cooling channels. So you can see these cooling channels are flat at the top. So here would also add support material. And in this case, this would be devastating, because this would be really hard to remove afterwards. So imagine this is also steel that is printed. So for these outer sections, here you could either remove it manually or mill it away. But in these inner sections, it would be really hard to remove. And then the cooling wouldn't work, of course. So what we would do, we would ask you to redesign the part, maybe add some material here, and just do the top more round, and then it would be able to print it. I won't go through all the different steps right now, but if you have any questions, please write them to me or give me a call or whatever. But this is a step that we always discuss together with the customer in order to improve the quality of the printed part. So what I'm trying to say is that we really want to reduce the amount of support material, because then we can shorten the production time, so we can decrease the cost of the part. We can use less material, once again, decrease the cost, and hopefully less machining afterwards and less manual work. And also you get an improved surface quality if you don't need support material. So imagine that you have support material and then you try to crack that off or you remove it, and that will affect the surface right here. And also you will contribute with less waste in the end. So another example for this part is that instead of adding a lot of support material, you could just orient the part upside down and then add this hole, because that will be there anyway, and then you could print it directly without adding any support material. So I'm not trying to do anything complicated here. I'm just saying that if you have any questions, please contact us in the beginning, and then we can look on your specific tool or your specific part, and we can give you some recommendations what to think about, or some recommendations on the part or how we would print the part in the best way. So please reach out to us directly if you have any questions about your tools or your parts. Next step to improve a part would be to do some slight redesigns or simulate maybe the cooling in the part or something like that. So here we can also help to design and simulate your parts. And what I mean with that is, so for plastic injection molding, we, like I said before, we redesign the cooling channels, and we do this based on simulations. So of course we can do it based on knowledge as well, but in order to get the best result, we always recommend to actually simulate the tool. So we simulate, we see where the hotspots are, we redesign the cooling channels, and then we simulate it once again and see if we should redesign the cooling channels once again, or if we are happy with the results. Another thing we can do is stress simulations. So we often do stress simulations to see that we don't have any internal stresses and that there's a small risk of cracking in the tool, especially if we do big redesigns like topology optimization. I will come back to this area later, but topology optimization is mainly where you try to remove all unnecessary material. And I will talk about that later. So there will be a cliffhanger for now. So a small customer case of how we work with design and simulations. So here we have a tool that was sent to us by a customer, and the tool has a crack in it. So it cracks at the same place every time, which you can see right here. So we did a simulation on the tool, on the original design of how it looked when we received it. And here you can see in 4 different points we have quite high stresses. So we did some redesigns and we modified the cooling channel, and we simulated it once again, and thereby we reduced the stresses. So the same cycle time, the same cooling, but just reducing the stress. So just to show you how much a simulation could help, not only by improving maybe the cooling, but also improving the lifetime of the actual tool. And if you want to take it one step further, then this is a quite complicated case where we have implemented topology optimization in the tool. So these two in the middle, they are topology optimized, where you can see a lot of material is missing compared to the 2 tools on the outer side right here. So I will go through the process shortly. I will just show you the application first. So these tools are producing a plastic part for the automotive industry, and it's right here under the car hood, and it's a distance piece so that the car hood is in the right distance to the car. The product is made out of polyamide 66, and the main problem with this product is that it has some really thick areas and some quite narrow areas, and that means that the cycle time is really long in order to reduce the warpage of the part. So the cycle time is quite long for this part originally. And that's why we redesigned the cooling channels, as you can see right here. So the goal was also to reduce some material because it's a quite big part. So first of all, what you do, you design the tool and you design all the mounting areas that you have to have. And of course, you design the cavity. And after that, you design the cooling channels. And then you have to know all the loads in the injection molding machine. So you tell the program where you're going to mount it. So these are areas that you can't remove. You also tell the program that this is the cavity. So here you can't remove any material either, of course. And you can't remove the cooling channels. And then you add all the different loads that are affecting the mold. And then we can calculate where we can reduce material. And this is quite interesting because imagine milling this tool. That would be really expensive. But when it comes to additive manufacturing, less material also means a cheaper cost to produce. So if we look on the original tool, it has a weight of 2.3 kilos. And when we have topology optimized the tool, now it only has a weight of 1.5 kilos. So what does this mean? Well, if we compare the conventional tool, the cost of producing that one was 5,000 euros. And if we were to print this exact design, then it would be 7,000 euros. But now when we have topology optimized the tool, we can print it for 6,000 euros instead. So this is a decrease of approximately 15%, I believe. And now for one tool, this might not be that much, but imagine that you have several tools or several cavities, and then you only need to topology optimize the first tool, and then you can just print the rest of the cavities. So if we look at the cycle time reduction, we went from 38 seconds to 23 seconds. And what does this mean? Yes, it means that already after approximately 20 or maybe less than 20,000 shots, then the tool is already cheaper than the conventionally produced tool. So that's the interesting thing with this case as well, that you don't need to produce millions of parts in order to print the tool. You can actually have a quite small production of parts per year and still use additive manufacturing. And last but not least, before going into all the other customer cases, I would just like to talk a bit about the post process. So of course, we always do powder removal before sending the part. And we also always remove the support material if there are any. We can always help with heat treatment as well, because we have heat treatment in-house, and also coating. So done in Denmark. In Denmark, we have a coating facility, and here we are happy to coat our inserts or tools as well. We can also do some sandblasting and analysis of the printed parts as well. And when it comes to quality control, and this is something that we don't do too often, to be honest, for plastic injection molding, but for oil and gas, this is quite common. And what we do is that we print test specimens on various places on the printing plate or the build plate. And these are printed to the same height as the part or the tool that we are printing. So that means that after we are printed, we can cut the specimens from the base plate, and then we can cut them into different heights. And then we can test the yield strength and the hardness at different heights of the printed part. So just to secure or to show you that the quality is even throughout the entire height and at different places on the build plate. So if we move on to some customer cases, the first one I would like to show you is the medical container. And here you can see that we went from almost 19 seconds down to 14 seconds. And the main issue with this product is that it has a really thin area down here, and then some quite thick areas up here. So if we look on the part, on the left side, you can see the conventional tool, and on the right side, you can see the 3D printed tool. And if you ask me, then I would say that this part is quite unnecessary to print because the cooling is already quite good in the conventional one. And also when you do plastic injection molding and the plastic solidifies, then it will actually shrink around the insert right there. So I would say that the insert is the main part to print because here you really want to have some good cooling, but also these moving sliders, these are also really important because here the plastic is much thicker than in the rest of the container. So if you would have asked me, I would recommend to print these two and probably not print this one because you can see there's a lot of mass right here. So this is quite expensive to print. If we look on the insert once again, and the insert is also a hybrid tool. So the customer mailed this part, and then the customer sent this part to us, and we put it into the AM machine, and we only printed the top of the part. And what does this mean in numbers? Well, we managed to reduce the cycle time with approximately 25%. And then if you look on various numbers of cavities, so if the customer had a 1 cavity tool, then they can produce 1.5 million parts per year. And if they have an 8 cavity tool, then they can produce 12 million parts per year. So of course, the printed tool is more expensive, but already at a 1 cavity tool, you can see that you can print a lot more parts and thereby have a bigger overall gain. And then the more cavities you have, the bigger your gain will be. But then also I think it's important to remember that you don't always have to increase your production, but maybe you can print less cavities. So maybe now they can go for 4 cavities instead of choosing 6 cavities or something similar to that. So it might also mean that you can produce your parts faster or with less amount of machines. That's also something to have in mind. Another thing I would like to talk about is vacuum bracing. So I will just show you vacuum bracing really fast. And it's mainly when you want to produce something that looks like this. So you have conformal cooling in a conventional way, and you produce it in steps. So you start with the bottom like this, and from here you can mill the cooling channels inside of the tool. And then you produce the top of the tool. You add them together in a furnace. So during high heat, then the two parts will brace together and become one solid tool. So why am I talking about this? Well, the reason to choose vacuum bracing, or the background for using vacuum bracing, is often because you want to reduce cycle time, or maybe you have some quality issues or warping problems, and you want to have a more uniform cooling. And these are the same reasons to choose additive manufacturing. Of course, you maybe don't always want to achieve all of them, but if you're looking for vacuum bracing, then the step to choose additive manufacturing, or at least looking at additive manufacturing, is quite short. So they're quite the background for choosing the two techniques is quite close to each other. Another positive thing is that if you're using vacuum brace tool, then you probably have done some sort of simulation, or at least optimized the cooling of the tool in some way. So if you're lucky, then you can print it straight away and it will work really good. Or you can optimize it even further with additive manufacturing. And I will show you a customer case on this later on. So what's the positive thing with vacuum bracing? Well, with vacuum bracing, you can produce quite a large tool. So you can produce larger tools in vacuum bracing, I would say, than in additive manufacturing. The downside with vacuum bracing is leakages or cracking. So we see a lot of vacuum brace tools that are leaking or cracking or not working correctly. And this is a problem which you can solve with additive manufacturing. So a case that you see right here, this is for a flat ironing handle. And it's produced in 2 parts. So first you produce it like this, and from here you can mill the cooling channels, just like the example before. But what I would like to show you here, that if you print the part instead, you can actually produce even more advanced cooling channels to get a even more uniform cooling. So what does this mean? Well, it means that you can either have a longer lifetime of the tool, because maybe it won't, hopefully it won't have any corrosion or crack like the vacuum brace tool, and you can even improve your cycle time even further. So if you're looking at vacuum brace tool now, please also take a look on additive manufacturing, because it can always help you in some way. Next case I would like to discuss is a insert made out of beryllium copper, because beryllium copper is often used when you can't have any cooling channels. So what we have done here is that we have added some ellipse-shaped cooling channels. So they are quite high, but they're really narrow. And this is of course not possible in a traditional way to drill cooling channels that looks like this. And here you can also see that even if you have beryllium copper that has a really high thermal conductivity, then a 3D printed part is still better at cooling, because you can use the cooling channels and you can also control the cooling in another way, which you can't with beryllium copper. So I will just skip some slides here because I see my time is running out, and I would also like to answer some questions. So I just want to summarize what I've shown you. And to start off with, if you're looking on a tool, please contact us so we can help you in the early stage. And there we can discuss the optimized way to print it, but also discuss some support material and how to improve the printability of the tool. And if you want to, we can also do some simulations, but this we have to discuss at the meeting, of course. But then we also have traditional services. So if something breaks, or if you have a part that you want to investigate, you can always send it to us and we can investigate it and hopefully find the failure behind the tool. But we also have printing recommendations of how to print our material with your printers. And if you don't have any printers, then we have our own production facilities where we can print parts directly to you. So that's all I had to say for the webinar.